Hi, welcome to my design tutorial. Today's subject is illusion of perfect geometry. Let's dive in to see what it means. In product design, true geometric shapes with their straight lines and perfectly rounded edges are often preferred over accelerating shapes. However, there are a few good reasons why not to make your geometry actually out of straight lines and constant radiuses. To allow the reflections to run smoothly with positive tension, the surfaces need to be slightly domed and transitions between surfaces need to be fluid. This positive surface tension is also important for compensating deformation during manufacturing. In the following, I will show you how to create this illusion of perfect geometry. In this tutorial, I use Solidworks, but these principles apply to all modeling software. Some programs may offer a different level of control and automated features, but with these principles, you should be able to construct your desired shapes in any software. Here on the right, you see a box that has been modeled using straight lines for all main surfaces and regular fillets for the corners. As you can see with the zebra lines turned on, the transition between the side and the corner fillet is abrupt. And in a physical product, you would be able to see a discontinuity here. In this model on the left, you see smooth continuity in the same surface transition point. This is the continuity we want to achieve. If you are a designer inspecting parts, it is important to understand that this is not a manufacturing defect, but a defect in a 3D file. We start off by defining the main dimensions of our box in a sketch. Note that I define the main dimensions and then use equations to define all the related dimensions. By doing this, your model updates much faster in case you need to change some of the dimensions. Next, I define the profile of my side surface. I use Arc tool to define this profile. I find a large enough radius that makes the line appear straight. Next, I define the cross-section of my surface in another sketch. If I already know that this will be a parting line in my injection molded part, I can define a draft angle here. I use the separate construction curve to do that. And as with the main profile, I use Arc tool to construct this curve. And I define the radius so that it looks almost straight. Then I use Sweep tool to construct this surface. Next, I mirror this master side surface to all four sides. Obviously, if your model wouldn't have proportions of a square like here, you would go and define your other side surface separately. Next, I move to construct my reference corner fillet. I start that by copying two of my side surfaces. I change the color of these copied surfaces to make them stand out. Next, I fillet these two copied surfaces. I adjust this fillet to what I want my final corner radius to be. This fillet is a regular circular profile fillet. I match the color of this fillet to my copied surfaces. The next step is to build our actual corner surface. Curvature continuous fillet command in Solidworks lacks tension control. For that reason, we are unable to match this surface to our target surface. I will anyways use this fillet tool to trim my side surfaces and construct the actual corner surfaces manually later on. The curvature continuous transition between two surfaces requires more space than a traditional tangent continuous surface like a regular fillet. That's why we have to start our corner surface further back. Next, I delete the fillet surfaces that I just created. Now I create my corner surface using boundary surface tool. I define the start and end points as curvature continues. Next, I extract the middle cross-section curve from my reference corner. I might need that as a guiding feature later on. Next, I adjust the tension values of my boundary surface. My aim here is to find the closest visual match to my reference surface. Make sure your tension values are same between the end and start point. Otherwise, you end up with an asymmetric design. This surface looks already pretty good. Next, I want to see if I can improve this surface by using the cross-section curve that we just created at previous step. But it looks like that in this case it doesn't really add that much value. So I will just continue with my previous design. So this surface looks pretty good now. But when I check it from different angles, I can see that it actually appears just a little bit too flat right in the middle. Now if I would just drive the tension values up, I would get rid of the flat middle section. But in fact, my corner would be much more pointy and wouldn't match my original reference surface anymore. To improve that, I will do two things. First, I move my starting point further back by adjusting my driver fillet. Then I drive the tension values up to match my original reference surface. You often need to go a little bit back and forth with these values to find your perfect match. Now I'm getting pretty happy with this surface, so I will just go ahead and copy this to all four corners. I knit the surfaces together and I turn the zebra graph on to check the continuity. This looks pretty good, so I move to construct my top surface now. Same way I created my side surfaces, I start with creating a straight construction curve to drive my surface curves. Once again, I use arc tool to create my profile curve. In this case, I want to be able to say how many millimeters my top surface is domed. So instead of defining the radius for the curve, I will define vertical distance from my construction curve. Next, I define my cross section. In this case, I want it to be identical to my main profile curve, because I want my top surface to be symmetric. Next, I use sweep tool to construct my top surface. Then I use trim tool to trim the excess surfaces. And now we are basically done. Before we stop, I want to show you one more extra thing. A lot of the products that I've worked on have these rounded half circle shapes, or what we call racetrack shapes. The way I construct these surfaces is exactly the same as I just showed before, with the exception that these surfaces always need this middle cross-section curve as an additional driver. So what you do, you define your start and end points as curvature continues. And then you define your cross-section as direction vector. And then you basically go back and forth adjusting your start and end point location and your tension values until you are happy with your surface. Thank you so much for watching this tutorial. Please do let me know what you thought of it and what kind of tutorial would you like to see next. Thanks, bye.